Let's have a look at some more Charles Law problems. Number 2 is a good reminder that we can't use just any temperature scale for Charles Law problems. It has to be the Kelvin temperature scale. And the reason for that is very simple. If we use Celsius and we start thinking that 0 degrees Celsius actually means no temperature, that's going to lead to some problems because we can in fact get colder than 0 degrees Celsius. We can get a lot colder. So Charles' law states that this ratio, volume over temperature, is a constant. So V1 over T1 is going to be equal to V2 over T2. The 1's and the 2's refer to two moments in time, the first moment in time and the second moment in time. Those variables are paired up together and measured at the same moment, and their ratios equal one another. So that's the essence of Charles' law. Charles' law also tells us that we have a directly proportional relationship when we use the Kelvin temperature scale. We still get a linear relationship if we use other temperature scales, but it's not directly proportional. Directly proportional means if we double temperature, then the volume will double. Okay, and really the only way to know if temperature is doubling is if you use the absolute temperature scale, the real temperature scale, which is Kelvin. Okay, so let's have a look at number 2 here. A sample of oxygen occupies 160 cubic decimeters. That's the same thing as liters, by the way. It's just a nice reminder that that's the exact same thing as a liter. 91 degrees Celsius, what will be the volume of oxygen when the temperature drops? Okay, so before we do anything, let's think about something that would be reasonable. How could we be reasonable about what we're doing here? Well, what's going to happen to the volume when the temperature drops? Okay, when you have a directly proportional relationship and the temperature is moving this direction, well, the volume is also getting smaller as well, right? Smaller temperature, smaller volume. If we cool off the gas sample, it's going to shrink a bit. All right, so let's list out what we know in this problem. The first volume is 160 liters. The first temperature is 91 degrees Celsius. Now we got to add 273 to know what that is in Kelvin. So 91 plus 273. 364 Kelvin. Okay. And our second volume, we're going to try to figure out. We don't know it, but we know the new temperature is going to be 0 Celsius. All right, with extra digits in there. I don't remember the digits on the Kelvin. I think it's 273.113 or 14. I've forgotten, but we'll just go with 273. All right, so we add 273 to 0. That's 273 Kelvin. Okay, and so these are the temperatures we need to be concerned with here, the Kelvin ones. Okay, so let's use Charles' law, plug in what we know. So here's Charles' law. We're going to solve for the new volume by multiplying both sides by T2. And that gives rise to T2 times V1 over T1 equals V2. Okay, so our second final temperature was 273 Kelvin. Okay, the original volume is 160 liters, cubic decimeters, and the original temperature, there it is, 364 Kelvin. All right, the Kelvin unit divides out, and so we're hoping to see a smaller volume, right? A smaller volume. And so let's type in 273 times 160 divided by 364. And we have 120. The unit is liters. Okay, and so this is a reasonable answer because it's a smaller volume. You have to use the Kelvin scale. If you think about it, if you plugged in 0 Celsius into what we're doing here and we cool it down to 0 Celsius, you know, that would give us a volume of 0, as if the gas didn't exist at all. But of course we could cool the gas further, so that's sort of a nonsense answer. So please continue on with the rest of the Charles Law problems.